Hello everyone, thank you for joining today's webinar. I am Sumit Singh, Product Manager for Electromagnetic Solution at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask your questions using the chat box option, and we will address all the questions at the end of the presentation. In today's webinar, we will cover various aspects of wireless power transfer systems, including its design challenges. We will also go through the EMS simulation and results. We will also have a live demonstration of the technology and Q&A session toward the end of the presentation. Wireless power transfer technology has gained significant interest in recent years due to its potential applications in various fields such as telecommunications, healthcare, and electric vehicles. Inductive and resonant inductive couplings are both types of near-field technologies that operate at a very short distance, usually a few millimeters to a few centimeters. These technologies work on the principle of magnetic induction, where an alternating current flowing through a transmitter coil generates a magnetic field. This magnetic field induces a current in a nearby receiver coil, which can then be used to power a device. Far-field technologies, on the other hand, operate over a longer distance, from several meters to several kilometers. Microwave and laser power transmissions are the two most common types of far-field technologies. In microwave power transmission, the power is transmitted through electromagnetic waves in the microwave frequency range, typically 2 to 3 GHz, while in laser power transmission, power is transmitted through the use of a focused beam of light. Wireless power transfer technology has a wide range of potential applications. One of the most significant applications is electric vehicle charging. This technology allows for static charging systems where vehicles are parked and charged wirelessly, as well as dynamic charging systems where electric vehicles can be charged while in motion. Next, we have wireless charging pads for smartphones and watches. This technology allows for easy and convenient charging without the need for messy cords or cable. Another application is implantable medical devices such as pacemaker, insulin pumps, and gastric stimulator can benefit from wireless power transfer technology. With wireless charging, patients can avoid the need for surgical replacement of batteries, making the process less invasive and more convenient. Wireless power transfer technology can also be used in industrial and domestic settings for mobile robots and drones. These devices can be charged wirelessly, allowing them to operate continuously without downtime for recharging. So, designing a wireless power transfer system is not without its challenges. We must consider several factors, such as one of the key design challenges is the effect of the air gap distance on efficiency. The efficiency of system decreases as the distance between the transmitter and receiver increases. Misalignment between the transmitter and receiver can also significantly reduce the efficiency of the system. A misaligned receiver may not receive enough power to operate, and a misaligned transmitter may waste power by transmitting it to the wrong location. Next, we have electromagnetic interference and compatibility is another critical design challenges for wireless power transfer systems. The system must not interfere with the other electronic devices in the vicinity and must be compatible with existing standards and regulations. Then the size and weight of the charger are also important design considerations. The charger should be small and lightweight enough to be easily portable while still delivering enough power to charge the device efficiently. Then wireless power transfer systems generate losses in heat, which can reduce their efficiency and lifespan. The system design must address these issues by using efficient components and cooling systems. So, the choice of shielding material can significantly affect the field distribution in a wireless power transfer system. The material should be chosen carefully to avoid interference with the magnetic field and to maximize efficiency. Finally, a successful wireless power transfer system must be adaptable and easily integrated into various power applications. The design should be flexible enough to accommodate different devices and power requirements. Moving ahead, in today's webinar, we will discuss about the wireless charger for implantable pacemaker. It is crucial to limit electromagnetic radiation and ensure that it does not exceed the standards established by healthcare organization. To simulate the wireless charger system in a realistic condition, we utilized a human body to serve as the receiver. To ensure maximum transfer power, both the transmitter and receiver operated at resonance. So, in order to illustrate the design of a wireless power transfer system for a pacemaker application, we have created a 3D model. The model includes a cross-section view of the system with equivalent coils. The two coils are aligned to ensure efficient power transfer. In addition to the 3D model, we have also created a simplified model of the wireless power transfer. The 2D model provides a clear illustration of the power transfer process between the transmitter and the receiver coil are aligned to ensure efficient power transfer. So with the help of this model, we have set up a study and run the simulation. Now in this section we will explore the effect of misalignment on the magnetic fields in a wireless power transfer system. To understand the effect of misalignment, we have created animation of the magnetic flux in 3 different situations. The first animation shows the magnetic flux in the system as the air gap distance increases. As the distance between the transmitter and receiver increases, the magnetic flux decreases, resulting in a decrease in the efficiency of power transfer. The second animation illustrates the effect of lateral misalignment on the magnetic flux. Lateral misalignment occurs when the transmitter and receiver are not perfectly aligned along the horizontal axis, as you can see in the animation. This misalignment causes a decrease in the magnetic flux and subsequent decrease in the efficiency of power transfer. And finally, the third animation shows the effect of angular misalignment on the magnetic flux. Angular misalignment occurs when the transmitter and receiver are not perfectly aligned along the vertical axis. This misalignment also causes a decrease in the magnetic flux and a subsequent decrease in the efficiency of power transfer. Next, as we know, the air gap distance between the transmitter and receiver in a wireless power transfer system can significantly impact the coil parameters, including inductance, resistance, and coupling coefficient. The first parameter we will look at is inductance. As the air gap distance between the transmitter and receiver increases, the inductance of the coils decreases, which results in a decrease in the efficiency. We can also similarly see the effect for the resistance. And finally, we have the coupling coefficient. The coupling coefficient is a measure of the magnetic coupling between the transmitter and receiver coils. As the air gap distance between the transmitter and receiver coil increases, the coupling coefficient decreases, again resulting in the decrease in the efficiency of power transfer. Moving ahead, we have also evaluated the effect of shielding on the field distribution of the coil. The use of shielding material can significantly impact and we can use a different type of shielding material such as aluminum, ferrite plates, or the combination of both. So if we look at the air core system, as you can see here, without any shielding material, the magnetic field is evenly distributed around the coils. Now let's add an aluminum shield to the same system. The aluminum shield will help to confine the magnetic field to a narrower space, resulting in a higher magnetic flux density around the receiver coil. Next, we have a system with ferrite plates. Ferrite plates are known for their high magnetic permeability, which helps to concentrate the magnetic field around the receiver coil. Finally, we have aluminum shielding of the system with ferrite plates. The combination of aluminum and ferrite plates provides the best of the both worlds, resulting in a highly concentrated magnetic field around the receiver coil. This effect of shielding helps us to reduce the power losses, protect the human body and electronic devices from electromagnetic interference, and also helps us to increase the coupling coefficient between both sides of the wireless charger. Next, when it comes to implantable medical devices, the shielding material can significantly impact the field distribution in the surrounding tissue. Let's take a look at a comparison with and without shielding. In the presence of shielding material, the magnetic fields is more concentrated around the wireless charger, hence resulting in a smaller region of high magnetic flux density in the surrounding tissue. On the other hand, without any shielding material, the magnetic field propagates in a larger area, resulting in a wider range of high magnetic flux density in the surrounding tissue. However, it is important to note that the use of shielding material may result in higher eddy losses, especially at higher frequencies. Therefore, the design of a wireless power transfer system for implantable medical devices must strike a balance between field concentration and eddy losses. It is also important to understand here is human body has a very low conductivity, but it increases with frequency. Therefore, the simulations are performed at two different frequencies, 20 kHz and 1 MHz. So if we look at the magnetic field distribution inside and around the human body at 20 kHz, as we can see, the field is relatively weak and covers a small area at this frequency. Now, if we look at the 1 MHz results, here the field is stronger and covers a larger area compared to 20 kHz frequency. This means that as the frequency increases, the magnetic field becomes stronger and can cover larger area in the human body. This effect should be taken into consideration when designing a wireless power transfer system, especially for implantable medical devices. Now let us take a look at the eddy losses and SAR results in the human body at 20 kHz. And as we can see from the graph, the eddy losses and SAR values are relatively low for 20 kHz. This means that as the frequency increases, the eddy losses and SAR values also increases, which can lead to potential health hazard in these devices. Therefore, it is crucial to consider the frequency effect on SAR and loss distribution while designing the system. Next, we have case study 2, where we'll discuss wireless power charger for electric vehicles and also go through its different pad topologies. Traditionally, inductive wireless power transfer systems are most commonly used for electric vehicles, and they are typically either circular or rectangular coils with ferrite plates. These topologies provide a single-sided magnetic field with one in and out path for the front of the coils. These Single-sided magnetic field topologies are important for electric vehicle charging systems because it provides a more efficient and effective transfer of power between the charger and the vehicle. The circular and rectangular coil topologies with ferrite plates are designed to minimize the air gap between the charging pad and the vehicle's receiver, which will maximize the power transfer efficiency. However, in addition to the circular and rectangular coil topologies with ferrite plates, there are also other pad topologies which are used in wireless charging systems for electric vehicle application. As we can see here, the first DD pad, the second DDQ pad, and the third bipolar pad are wireless charging pad topologies that offer certain benefits over traditional circular and rectangular coil topologies. DD pad has two sets of D coils as facing each other, which increases the coupling coefficient and improves charging efficiency. It also allows for greater tolerance for misalignment between the transmitter and receiver coils. Whereas DDQ pad is similar to DD pad but with a phase difference between the coils. This leads to a more uniform magnetic field and further improves charging efficiency. And then finally, bipolar pad has two coils, each with a separate magnetic pole, which increases the magnetic field strength and improves charging efficiency. It also allows for bidirectional charging, meaning the vehicle can both receive and transmit power. Overall, these pad topologies offer best charging efficiency, greater tolerance for misalignment, and additionally features such as bidirectional charging for bipolar pad. So now we'll compare the coupling coefficient of different pad topologies used in wireless charging systems. We have used EMS3D to compute the coupling coefficient for each of these topologies under two different conditions, at 0 alignment and at 0.5 meter of misalignment. When there is no misalignment, the DD pad, bipolar coil, and DDQ pad topologies show similarly higher coupling coefficient, all above 0.5. However, the single rectangular coil has a lower coupling coefficient below 0.3. If the receiver is misaligned by 0.5 meter away from the axis of the transmitter, the coupling coefficient drops for all the topologies, having the highest coupling coefficient under the bipolar and DDQ pad topologies have the highest coupling coefficient under this condition. We can conclude that bipolar pad and DDQ pad topologies have comparable coupling coefficients, but the DDQ pad topologies add an additional coil which increases the size and cost of the charger and may also increase heat generation due to the additional coil losses. So in summary, we'll compare the performance characteristic of different wireless charging pad topologies used in electric vehicles. The key parameter we'll look at are misalignment tolerance, coefficient of coupling, EMF exposure, and magnetic flux, and effect of shielding on the coupling coefficient. So starting with, the circular pad has poor misalignment tolerance and a low coefficient of coupling. However, it provides high EMF exposure and a low shielding effect, making it a single-sided pad topology. Moving to the DD coil, it has a poor misalignment tolerance but have a high coefficient of coupling. This EMF exposure is low and the effect of shielding on the coefficient of coupling is high, and it is a double-sided pad topology. Moving next to DDQ coil, has a high coefficient of coupling and a high misalignment tolerance. However, it has a low EMF exposure and high shielding effect. Like the DD coil, it is also a double-sided pad topology. And finally, The bipolar pad has a good misalignment tolerance and a high coefficient of coupling, but it provides low EMF exposure and high shielding effect. It is also a kind of a double-sided pad topology. In terms of magnetic flux, the DDQ coil and bipolar pad provide the highest magnetic flux. However, the DD coil is more expensive and generates more heat due to an additional coil. So in this simulation, we will be focusing on the design of a wireless power transfer using a double-sided power bipolar pad topology. The system comprises two overlapped lumped coils on the both transmitter and receiver side, with each coil consisting of 5 turns of wire with an 8 mm diameter. The ferrite support material is made up of AISI steel, and an aluminum shielding is added for extra protection. To ensure the system operates at maximum power and efficiency, we will analyze LCC Compensation Network with a voltage magnitude of 424 volt and a frequency of 85 kHz. The simulation will be performed using EMS 3D, which can be solved within Autodesk Inventor or SolidWorks. By analyzing the performance characteristic of this design as shown on the right hand side, we can evaluate its misalignment tolerance, coupling coefficient, EMF exposure, effect of shielding on coupling coefficient, and magnetic flux. This will give us a better understanding of the overall efficiency and effectiveness of the wireless power transfer EV charger. Now let's take a look at a double-sided LCC compensation circuit. This circuit consists of 3 components: a series inductor, a parallel capacitor, and a series capacitor. The LCC circuit is connected in parallel with the primary winding of the transmitter coil. The output voltage of the network is connected to the load. An optimized circuit layout can be created using the EMS software, which can be coupled with a circuit simulation tool to analyze the LCC network performance. The equivalent circuit schematic for the LCC network can be drawn to represent the circuit elements and their connections. The circuit diagram includes the value of the inductance, capacitance, and resistance of the component, as well as the power supply and load resistance. So the one way to analyze the performance of wireless power transfer system is to plot the input and output power as a function of frequency. This allows us to determine the resonant frequency at which the system operates most efficiently. So to create this plot, we can use simulation tool, and we can specify the parameters such as the transmitter and coil receiver geometries, and then we can simulate at a different range of frequency. The result of the simulation can then be used to generate this plot as an input and output power as a function of frequency, as well as the power efficiency as shown on the right hand side of the plot. This plot can provide insight into the optimal frequency range for efficient power transfer and can be used to optimize our system. As we can see here, the input power is close to 60 kW at 85 kHz, and the output power is around 56 kW. Another way is to evaluate the resonant frequency at 85 kHz is to visualize its magnetic field distribution inside and around the coils. This is due to the fact that the reactive impedance of the circuit is at its minimum. This will lead us to a better transfer of power from the transmitter and the receiver. So the magnetic field lines, as can be seen here, are concentrated in the region between the transmitter and the receiver coils, with the strength of the field decreasing as we move away from this central region. The magnetic field is highly localized and penetrates only a small distance into the surrounding environment. Moving ahead, we have also evaluated the electromagnetic losses occurring in the material, which when they are subjected to a changing magnetic field, and which in turn produce heat and cause energy losses. On the right hand side, we can see the core losses occurred in material like ferrite bars that are used to guide and shape the magnetic fields in the system. This causes the material to absorb energy and leading to energy losses and heating. Below we can see the winding losses occur due to the resistance of the wires. When current flows through the wires, they heat up and lose energy due to the resistance. These losses are proportional to the square of the current, so reducing the current flow through the wires can help to minimize these losses. Next, it's very important to understand the temperature distribution in the system, and simulating the temperature distribution in different components can help us understanding the thermal behavior and identifying any potential overheating issues. So the ferrite core and aluminum shields are important components to consider, as they can experience significant temperature rise due to the eddy current and hysteresis losses respectively. The temperature in the coil is important to monitor, as it can affect the efficiency and the output power. It is also very important to evaluate the distribution of temperature variation versus time, as the system can heat up during operation and can lead to overheating if not controlled properly. So this can be done through a thermal simulation of the system, where the temperature variation can be tracked over time and analyzed for any potential issues. So we have used our software and evaluated it at different time situation. Next, I would like to quickly demonstrate our software EMS and how do we perform the analysis. So our product comes as an add-in tool to the SolidWorks. So once we are inside the SolidWorks platform, we go to tools and then click on the EMWorks product and launch the EMS from here. Once the EMS product is launched, you'll be able to see the EMS manager right beside the SolidWorks manager tabs. So the first step is to either create a sketch for a wireless power transfer system, or you can import directly into the SolidWorks. Once the sketching is done, you have to simply click on the EMS manager. Here you can right click on the model, create a study as per your requirement, and once the study is created, the first step is to set up the material for all the components of your wireless power transfer system, such as the shielding, the coils. Once the material is set up, you need to excite these coils, and you can see the direction of the coil for different coils. So once the coil is set up and for the different receiver and transmitter, the next step comes to set up the mesh. You can easily use our mesh control feature to control the mesh element at different part of your wireless power transfer. So here we can see the mesh of our geometry. Once the mesh setup is done, next step is to set up the circuit for the analysis, and here we have created a LCC resonant circuit as shown here. So this is our LCC network for the primary winding of the receiver and the secondary winding of the transmitter. Once the circuit is set up, you can go ahead and run your analysis. Once the simulation is finished, you can look at the result into the result table section, where you can visualize its inductance, flux linkages, impedance, coupling coefficient, current, induced voltage, and many more. You can also visualize its magnetic flux density. You can also animate these flux density with versus phase. So here we have the animation for our system. You can also similarly look at its current density, force density, and electric field and loss density of the system. So, in conclusion, EMWorks solution provides a powerful platform to design and analyze wireless power transfer systems. The different topologies of wireless power chargers are used in different applications, were successfully explored and analyzed using EMS simulation. The main wireless power transfer design challenges such as misalignment tolerance, coupling coefficient, and EMF exposure were also investigated. The LCC circuit was modeled and simulated using the integrated EMS circuit simulator to improve the efficiency of the system. Power and efficiency were also calculated, and for optimal performance, we also look at its losses and heat generated using thermal solver to ensure the charger's safe operation and longevity. So in overall, EMWorks solution provides a comprehensive approach to design, analyze, and optimize wireless power transfer system for various applications. Here are the references that we referred for our today's webinar. And thank you so much for attending today's webinar.